Welcome back to the Deep Dive, where we take the crucial, complex components of enterprise technology, distill them down, and give you the foundational knowledge you need to be technically fluent and ready for action.
Today, we are moving past the theoretical basics of network connectivity. We're drilling down into the technology that really underpins every modern, scalable, secure corporate environment. Virtual LANs or VLANs. If you've sort of mastered the concept of a switch forwarding frames, now it's time to master the art of layer 2 segmentation.
That's right. Our mission today is a comprehensive deep dive into implementing and troubleshooting VLANs and, critically, VLAN trunking. We've collected a stack of sources that cover, well, everything from the 802.1q header structure to the critical DTP negotiation pitfalls.
Yeah, this isn't just about reading commands off a sheet.
No.
It's understanding the mechanisms of separation, why things work the way they do.
Okay, let's unpack this. We have to start with the fundamental why this technology even exists. Because the concept of a local area network, or LAN, it quickly runs into a hard limit in the real world.
Exactly. When a network engineer defines LAN, what they're really talking about is all devices that reside within the same broadcast domain. This is the fundamental constraint we have to overcome.
And what defines that broadcast domain in, like, a default setup? If you pull a brand new switch out of the box,
Right.
every port on that switch is essentially interconnected at layer 2. If a host sends a broadcast frame, an ARP request, maybe,
Common example.
that frame, by default, will just flood out every single active port on that switch. Every host hears it, whether it needs to or not. It's noisy.
Precisely. And, historically, if you needed to keep Department A's broadcast separate from Department B's, the only foolproof way was physical separation, like literally buying one physical switch for Department A
Right.
and a completely separate physical switch for Department B.
Which must have been incredibly expensive and complex to manage.
It solved the problem,
Yeah.
but introduced huge costs and management complexity.
Yeah.
Not scalable at all.
So the aha moment of the VLAN is that it allows us to create those completely separate broadcast domains, those virtual switches, all within the casing of a single physical device.
It's abstraction at its finest,
Yeah.
really. By configuring a port to belong to, say, VLAN 10, the switch physically restricts the forwarding logic.
Okay.
The internal logic of the switch treats ports configured into different VLANs as if they were on totally separate, disconnected layer 2 fabric. A frame originating in VLAN 10 will never be forwarded directly by the switch to a port in VLAN 20, regardless of the MAC address.
That separation is absolute at layer 2, and the benefits derived from this are, well, they're what makes VLANs pretty much non-negotiable in any modern enterprise environment.
Definitely. The first and probably the most easily quantifiable benefit is performance. Think about a modern data center with potentially hundreds, maybe thousands of devices.
Right.
Every time a broadcast frame is sent, every single device in that domain has to interrupt its CPU to process that frame, figure out it's not for them, and drop it.
That's a lot of wasted cycles.
Huge amount. By segmenting the network into smaller VLANs, we significantly reduce that broadcast noise, minimizing unnecessary CPU overhead on every single host. It just makes everything run smoother.
Which flows immediately into security. I mean, a
Yeah.
smaller broadcast domain means that when a device floods traffic, whether it's a broadcast, maybe multicast, or an unknown unicast address, fewer hosts actually receive that traffic.
Exactly.
If I can limit my finance department traffic to just the finance VLAN, I've instantly isolated that sensitive data from, say, the entire engineering department, even though they might share the same physical wiring closet.
And what's more, security teams can apply distinct granular security policies per VLAN. Think access control lists, ACLs, applied at the routing boundary between VLAN 10 and VLAN 20. They can be very precise.
Yeah.
You can define exactly what types of traffic are allowed to pass between specific work groups, which is just impossible in a single flat network.
Beyond performance and security, there's flexibility. I remember before VLANs, moving a user from one department to another, if those departments were tied to specific physical switches in the wiring closet,
Oh, yeah.
it often required physically moving the user's cable drop or even installing new infrastructure. A real headache.
Total headache. Now, location doesn't really matter in the same way. You can group users by department, function, or role, completely independent of their physical connection point on the floor.
So a new hire can sit anywhere.
Pretty much. A new hire can sit next to anyone else, and a quick remote configuration change, just reassigning their access port to the correct VLAN, places them instantly in their necessary network segment. This massively reduces IT time spent on moves, adds, and changes.
And for the administrator running the show, troubleshooting is fundamentally improved, isn't it?
Oh, absolutely. If a problem occurs, say a rogue DHCP server starts skewing addresses or you get a broadcast storm, the failure domain is contained entirely within the limits of the affected VLAN.
So it doesn't take down the whole network.
Exactly. This rapid isolation cuts down mean time to repair dramatically. You know where to look first.
Lastly, a point may be often overlooked but critical in large-scale deployments. Spanning tree protocol, STP, workload reduction.
Yes, STP, the protocol that prevents those nasty layer 2 loops. Historically, a single large broadcast domain meant a single massive STP domain, which could be unstable and, frankly, slow to converge after a change.
But with VLANs, we typically run per VLAN spanning tree, right? PVST or PVST plus beer. Can you explain how this segmentation helps reduce the protocol's burden?
Absolutely. It's quite elegant. Each VLAN now runs its own independent instance of the spanning tree protocol. Imagine a large switch block with, say, 20 VLANs.
Okay.
Instead of one huge, complex STP domain trying to calculate a single root bridge for the entire network, we now have 20 separate, smaller STP domains running concurrently.
Ah, so each one is simpler.
Much simpler. And if you design the network well, often limiting a specific VLAN to just a few access switches, you massively simplify the conversions path for each instance. Smaller domains mean faster reaction times and far less chance of cascading failures if an administrator happens to misconfigure a single link somewhere. It adds resilience.
Okay, VLANs are essential for local segmentation, that's clear. But they also create a new problem when the network scales beyond just a single switch. How do we get the traffic for VLAN 10, 20, and 30 from switch A over to switch B without burning through all our physical connections?
Right, this is the scaling problem that trunking was specifically designed to solve. If we did not use trunking, every time you needed a specific VLAN, let's say VLAN 10 for sales to span from SW1 to SW2, you need one dedicated physical cable running between those switches, assigned solely to VLAN 10 access.
I can immediately see the physical constraint there. If my core switch needs to support 20 different workgroup VLANs across maybe 10 distribution switches,
Yeah, think about the math.
I would need hundreds of physical links and literally thousands of switch ports dedicated just to switch-to-switch connectivity. That's cable sprawl and port consumption gone absolutely mad.
Completely unfeasible in any reasonably sized network. The solution, therefore, is VLAN trunking. Trunking uses a single physical link, often a very fast one, like 10 gigabit Ethernet, or even faster these days, to carry frames belonging to multiple VLANs simultaneously.
Okay, but how does the receiving switch know which frame belongs to which VLAN if they're all sharing the same pipe?
That necessitates VLAN tagging. Since the physical wire is shared, the sending switch must append a specific marker to the frame before sending it across the trunk. This marker tells the receiving switch exactly which broadcast domain that frame belongs to.
And that marker is the trunking header.
Correct. The sending switch inserts this header, which contains the crucial VLAN ID, before sending the frame across the trunk link. When the receiving switch gets the tagged frame, it reads that VLAN ID from the header, strips the header off, and then forwards the original clean frame only out the appropriate ports on its side. Say, only the ports configured for VLAN 10 in our example.
Now, the mechanism of tagging has been standardized globally, hasn't it? I know Cisco historically pushed its proprietary interswitch link ISL protocol.
It did, yes. ISL was Cisco's early attempt.
But today, ISL is largely deprecated, right? You often don't even find support for it on modern hardware.
That's generally true. The undisputed champion, the industry standard, is IEE 802.1Q, often just called .1Q.
.1Q?
802.1Q is the encapsulation we really care about. Let's look closely at its structure for a second. It inserts a small but very powerful 4-byte header right into the original Ethernet frame header.
Where exactly does it go?
Specifically, it gets inserted right after the source MAC address field and just before the original Ether-type link field.
So that 4-byte insertion means the frame actually gets slightly bigger, up to 4 bytes larger than the standard 15, 18-byte maximum Ethernet frame size.
Correct. Switches and links need to be able to handle these slightly larger baby giant frames. And within those 4 bytes, there are several fields, but the one that truly defines the separation, the core of it, is the 12-bit VLAN ID field.
12 bits. Okay, that number is interesting because mathematically, 2 to the power of 12 gives us 4,096 unique possibilities. But you mentioned earlier we can't use all of them, right?
Right. You can actually use 4,094 of them for user VLANs. The values 0 and 4095 are reserved by the standard and therefore unavailable for assignment to access ports or standard VLAN configuration.
Ah, okay. That's a key detail. Why are those specific numbers set aside? What are 0 and 4095 used for?
While VLAN ID 0 is often reserved for special situations, sometimes involving priority indication or specific filtering mechanisms. It can sometimes be used by switches to indicate that the frame is untagged, but still carrying layer 2 priority markings using the other bits in the 802.1q header, like for quality of service, QoS, without needing explicit VLAN membership.
I see. And 4095.
VLAN ID 4095, the all ones address in binary, is generally reserved for internal switch functions, maybe testing, specific internal forwarding loops, or proprietary filtering mechanisms within the switch hardware itself. They're functional numbers within the protocol, just not IDs you can assign to a user group.
That distinction explains the practical limits we work with. And in the Cisco world, those 4094 usable IDs are often split into two ranges, aren't they?
Yes, there's the normal range, which is VLAN IDs 1 through all 1005. This range is generally sufficient for most small to medium enterprises.
Okay.
Then there's the extended range, covering IDs 1006 all the way through 4094. Using these requires switches that support them, and sometimes has implications for older protocols like VTP, which we'll touch on.
And this discussion of tagging and IDs leads us directly to the concept that often confuses people when they first learn this. The native VLAN.
Ah, yes, the native VLAN. 802.1q defines one specific VLAN, and by default, this is almost always VLAN 1 as the native VLAN for a given trunk link.
What exactly is happening on the wire when a frame belonging to the native VLAN crosses that trunk? How is it different?
It is sent completely untagged. It does not receive that 4-byte 802.1q header.
Okay. But why? If the whole point is tagging for separation.
The rationale is pretty simple, actually. The receiving switch knows it is receiving frames on a configured trunk link. If a frame arrives on that trunk without an 802.1q tag, the switch simply assumes it must belong to whatever VLAN is configured locally as the native VLAN for that trunk.
But if the entire goal of 802.1q is explicit separation through tagging, why did the IE standardize what seems like a loophole? It feels like it risks mixing traffic, even if it's just for compatibility.
It really boils down to being a necessary backward compatibility feature. Imagine connecting a brand new, modern switch running 802.1q trunking to, say, an older layer 2 hub, or maybe a simple switch that doesn't understand tagging at all.
Or even just a misconfigured port on the other side.
Or a misconfigured port, exactly. By sending frames from the native VLAN untagged, we ensure that at least that one specific VLAN can traverse the link without being dropped by the legacy or non-tag-aware device.
Ah, okay. So it maintains a very rudimentary level of connectivity.
Precisely. It allows non-802.1q traffic, or traffic destined for the native VLAN segment, to flow across what is otherwise a fully segmented, tagged link. However, as we'll definitely dig into in the troubleshooting section, this feature is also the source of one of the most significant Layer 2 security vulnerabilities, VLAN hopping.
Right, so we've segmented our network beautifully within switches using VLANs, and we've scaled that segmentation across multiple switches using trunking and tagging. Now for the ultimate connectivity challenge. Getting Fred over in VLAN 10 to actually talk to Betty, who sits in VLAN 20. The separation worked almost too well.
Exactly. This highlights the core functional limitation of Layer 2 switching. Switches operate based on MAC addresses, and they perform that forwarding within a specific VLAN. They're simply not designed, nor are they capable, of forwarding packets between two different broadcast domains.
They're like separate universes.
By design, completely separate universes at Layer 2, VLAN 10 and VLAN 20 might as well be on different planets as far as the switch's all-2 logic is concerned.
Okay, so since they are separate Layer 2 domains, that implies they must also reside on separate IP subnets, correct?
Absolutely. That's a fundamental rule.
Okay.
Devices in different VLANs must be in different IP subnets. And whenever a packet needs to move from one IP subnet to another,
You need routing.
you absolutely require a Layer 3 device. Traditionally, this is a dedicated router, but nowadays it's often a Layer 3 switch, also called a multi-layer switch.
Can we trace the path? Let's say Fred in VLAN 10, subnet 10, wants to send a packet to Betty in VLAN 20, subnet 20. What happens step by step?
Sure. So Fred's PC looks at Betty's destination IP address, compares it to its own IP address and subnet mask, and realizes, hey, this destination is not on my local subnet.
So it needs to go to the gateway.
Exactly. Fred's PC encapsulates the IP packet into an Ethernet frame, But the destination MAC address it uses is not Betty's MAC address. It's the MC address of its configured default gateway, which is typically the router's interface IP address assigned to subnet 10.
Okay, so the frame goes to the router's MA. What does the switch do?
The switch receives Fred's frame. It looks up the destination MA, the router's MS, in its MA address table for VLAN 10, and forwards the layer 2 frame out the correct port towards the router. This might be a physical port connected to the router, or if using a layer 3 switch, it's handled internally.
Now, the frame hits the layer 3 device. This is where the magic happens.
This is the crucial step. The router, or L3 switch, receives the layer 2 frame on its VLAN 10 interface, or SVI. It strips off the Ethernet header, exposing the layer 3 IP packet inside. It then looks at the destination IP address within that packet, Betty's IP. It performs a routing lookup in its routing table, finds the route to subnet 20, and determines the exit interface should be the one associated with VLAN 20.
But it can't just forward the original frame?
No, because the layer 2 information is wrong for the new segment. The router performs a vital step, re-encapsulation. It crafts a brand new layer 2 Ethernet frame. This new frame still contains the original IP packet, but now the source MAC address is the router's MC for the VLAN 20 interface, and the destination MAC address is Betty's actual MAC address, which the router finds via ARP in VLAN 20.
Ah, so it builds a completely new L2 wrapper for the L3 packet.
Precisely. The switch then takes this new layer 2 frame, sees it's destined for Betty's MC within VLAN 20, and sends it out the appropriate access port in VLAN 20, where Betty finally receives it.
That whole process, receive L2, strip, we're at L3, re-encapsulate into new L2. That's the essence of Inter-VLAN routing.
That's it. Historically, we often called this the router on a stick model. You have a single physical router interface configured as an 802.1q trunk, carrying tagged frames for multiple VLANs using logical subinterfaces, one per VLAN.
I remember configuring those.
Yeah, lots of subinterfaces. Today, modern networks more often use the layer 3 switch that performs this routing function internally, much faster, using switched virtual interfaces, or SVIs. An SVI is basically a virtual layer 3 interface representing each VLAN within the switch itself.
Much more efficient, but the underlying layer 3 routing principle remains identical. You need that L3 hop.
Always need the L3 hop between VLANs.
Okay, let's nail down the configuration basics now, starting with the simplest case. Access ports. If you can't get the host connected to its VLAN correctly, none of this routing matters.
Right, fundamentals first. Configuration is usually a two-part process. First, you need to actually define the VLAN globally on the switch. The command is VLAN.
So VLAN 10.
Exactly. And then it's highly recommended to give it a descriptive name using the name command, like name sales depth.
The sources stress this naming part. Why is it so important? I mean, the switch will often auto-create a VLAN if you try to assign a port to one that doesn't exist yet, won't it?
It will, yes. If you just go to an interface and type switch port access VLAN 10 and VLAN 10 doesn't exist, the switch will typically create it. But it gets a default generic name like VLAN 0000.
Which isn't helpful when troubleshooting later.
Not at all. Relying on auto-creation leads to confusing configurations. Intentional creation and naming makes the network documentation self-evident and troubleshooting much, much easier down the line. Take the extra 10 seconds to name it.
Good advice. So step 1, define and name the VLAN. Step 2 is assigning the interface.
Right. You go into interface configuration mode for the specific port and use the command switch port access VLAN ID number. So switch port access VLAN 10 assigns that port to the sales VLAN.
And critically, many engineers also add the command switch port mode access. Why is that specific command so important? Doesn't assigning the access VLAN imply it's an access port?
It does imply it, but switch port mode access does two critical things explicitly. First, it locks the port down, ensuring it always operates in access mode, never attempting to become a trunk.
Okay.
Second, and arguably more important, it explicitly disables the dynamic trunking protocol DTP negotiation on that port.
Ah, DTP. We need to talk about that.
We do. If you leave a port in its default state, which is often dynamic, DTP is active. This could potentially lead to instability or even a security issue if the device connected to that port unexpectedly tries to negotiate a trunk. Statically configuring switch port mode access prevents that ambiguity. For access ports, static is almost always preferred.
Makes sense. Secure and unambiguous. Okay, that brings us neatly to the complexities of trunking modes and this dynamic trunking protocol, DTP. Configuring a trunk is more nuanced, isn't it? It involves not just the encapsulation type, like 802.1q.
Right, you usually set that with switch port trunk encapsulation.1q. Although on many modern switches, .1Q is the only option, so it might be the default.
But also this crucial administrative mode that dictates how the port behaves in terms of negotiation.
Exactly. DTP is Cisco's proprietary protocol designed to automatically negotiate whether an Ethernet link between two capable devices should become a trunk or remain an access port.
So it tries to figure it out automatically.
It tries. And we have 4 key administrative modes you can set
Yeah.
using the switch port mode command. The 2 static modes are straightforward. Access means it's always an access port, never a trunk. Trunk means it's always a trunk port, never an access port. These don't use DTP negotiation.
Simple enough. Then we have the 2 dynamic modes.
Right. Dynamic, desirable, and dynamic auto. These are where things often go wrong if you're not careful.
Okay, what's the difference? Desirable versus auto.
Think of dynamic desirable as the active initiator. A port set to desirable actively sends DTP messages out onto the link saying, "Hey neighbor, I'd like to form a trunk with you. What do you think?"
It's eager to trunk.
Very eager. Dynamic auto, conversely, is passive. It just sits back and listens. It will respond positively and agree to form a trunk if its neighbor sends a desirable message asking to trunk. But critically, a dynamic auto port will never initiate the trunking negotiation itself.
It waits to be asked.
Precisely. It waits to be asked.
What's fascinating here is the logic behind the operational results, especially when you have misconfigurations or rely on defaults. This negotiation matrix is absolute gold for troubleshooting.
It really is. The classic pitfall, the one that bites almost everyone starting out, is when both switches connected together are left at their default DTP setting. And on many Cisco switch models, that default is dynamic auto.
So you have auto facing auto. What happens?
Well, since neither side is initiating the conversation, both are passively waiting to be asked, they both eventually time out waiting for a DTP negotiation message. They conclude, well, the other guy doesn't want a trunk, and they both default to operating as simple access ports.
Even though they're connected switch to switch.
Even though they're switch to switch and potentially capable of trunking, the result, the link comes up, looks fine physically, but it remains operationally in access mode. And guess what? None of your tagged VLAN traffic, anything other than the native VLAN, will cross that link.
That is the crucial insight. A link between 2 switches will only successfully form an operational trunk if at least one side is configured to be active in the negotiation, meaning it's set to either static trunk or dynamic desirable.
Correct. If you see a switch-to-switch link that is physically UPU, but only traffic in the native VLAN seems to be working, your very first check should be the show interfaces switch port command on both ends. Compare their administrative and operational modes against that DTP negotiation matrix. Chances are high you've got an auto-auto or some other non-trunking combination.
Before we move on from configuration, we probably have to briefly talk about VLAN trunking protocol, VTP, even if, as you said, it's becoming less common or actively discouraged in modern network architecture.
Yeah, we should mention it. VTP is Cisco's proprietary tool designed to automatically advertise and synchronize VLAN configurations. Just the VLAN ID and name, not port assignments, across a local network domain connected by trunks.
Sounds convenient on paper, maybe. Keep all the switches consistent.
It can be in very specific controlled environments, but its potential risks often outweigh its rewards, which is why many organizations are deprecating it, disabling it entirely, or simply setting all switches to VTP transparent mode.
Okay, tell us about the modes and the risks.
There are 3 main VTP modes. Server mode is where you can actually create, modify, and delete VLANs, usually limited to the standard range, 1005. The server then advertises these changes to other switches in the same VTP domain.
Okay.
Client mode switches cannot make any local VLAN changes. They passively listen for advertisements from a VTP server in the same domain and update their local VLAN database accordingly.
So they just learn.
They just learn. And finally, transparent mode. A switch in transparent mode doesn't participate in VTP synchronization. It doesn't advertise its own VLANs, except maybe forwarding received VTP messages, and it doesn't synchronize its database based on received advertisements. You can configure VLANs 1-40094 locally on a transparent switch, and those changes only affect that local switch.
Transparent mode seems like the safest default if you're not actively managing a VTP domain.
It generally is. It isolates the switch from accidental domain-wide changes. The absolute critical security warning here relates to something called the VTP configuration revision number.
Ah, the revision number. How does that cause problems?
Yes. When a VTP server sends out an advertisement with its VLAN list, it includes a configuration revision number. Switches in the domain will only accept and apply a VTP update if the incoming advertisement has a higher revision number than the one currently stored in their own database.
So higher number means newer configuration. Makes sense.
It does, but here's the danger. Imagine you take an old switch off the shelf, maybe one that was previously used in the network. Perhaps you do a basic factory reset, but maybe the revision number stored in NVRAM doesn't get fully cleared, or you just plug in a brand new switch configured as a server with a default, often 0 revision number, but then you delete all VLANs, creating a new revision.
Okay.
Now, if this switch, configured as a VTP server, gets connected to your production network, and it happens to have a stored revision number that is higher than the current revision number used by your actual production VTP server,
Oh, no.
it will send out its configuration, which might be an empty list of VLANs if it was reset or newly configured without VLANs. And because its revision number is higher, every client and even other servers in the VTP domain will accept this update
And they'll delete all their production VLANs based on this road advertisement.
instantly. Network-wide VLAN database wipe. Complete outage across the entire VTP domain. This is why VTP is treated with extreme caution. Best practice is often to disable it using transparent mode, carefully manage VTP domain names and passwords if used, and never experiment with VTP server mode on any switch connected, even indirectly, to a production network without fully understanding the current domain revision number. The potential for catastrophic accidental damage is just too high.
Let's shift gears now to a really specific but very common application of VLANs that cleverly solves a very real logistical problem: the rise of IP telephony, VoIP phones.
Ah, yes, this is a perfect example of how technology evolution sometimes bumps up against physical constraints. Before IP phones became the standard, most offices needed 2 separate cable drops to each desk. One for the traditional analog phone line and one for the PC's Ethernet connection.
I remember those days. 2 jacks at every cube.
Right. But when IP phones came along, they also needed an Ethernet drop. The problem was, most existing office buildings only had that one Ethernet cable running to each desk location. Running a second, brand new Ethernet cable to every single desk was often financially prohibitive, disruptive, and just a massive undertaking.
Yeah. Pulling new cable through existing walls and ceilings is expensive, messy work. That logistical pain really drove the need for a smart technical solution, didn't it?
It absolutely did. And the solution was quite elegant. Embedding a small, functional 3-port Layer 2 switch right into the base of the IP phone itself.
A switch in the phone.
Effectively, yes. So now, this single Ethernet cable coming from the wiring closet switch plugs into one port on the phone, the network or switch port. Internally, a second port connects directly to the phone's own processor and network interface, and the third port acts as a standard Ethernet port facing the user, providing a connection for the user's PC sitting right there on the desk.
Clever. So you daisy-chain the PC off the phone using that single drop back to the closet.
Exactly. But now you have 2 different types of devices, the PC and the phone, sharing that single physical connection back to the main switch port in the closet. And these devices have fundamentally different network requirements.
How so?
Well, the PC traffic is typically standard data connectivity, web browsing, email, file shares, which is often bursty and can tolerate a bit of delay. It's often treated as best effort traffic.
Okay.
The voice traffic from the phone, however, is real time. It's highly sensitive to network delay, latency, and variations in delay, jitter. For a clear phone call, that voice traffic needs special treatment, usually involving quality of service QoS mechanisms.
So you can't just dump them both into the same VLAN without potential problems for voice quality.
Precisely. The widely accepted best practice, strongly recommended by Cisco and other vendors, is to separate the 2 types of traffic logically. Put the PC's data traffic into a dedicated data VLAN, sometimes called the access VLAN in this context, and put the phone's voice traffic into a completely separate voice VLAN.
Okay, so we need 2 VLANs traversing that single link between the closet switch and the phone. This sounds like the switch port connected to the phone needs to act like some kind of hybrid, doesn't it?
It does. For the PC traffic, the switch port must essentially act as an access port. The PC itself is usually VLAN unaware. It just sends standard untagged Ethernet frames. The switch needs to receive these untagged frames coming from the PC via the phone's pass-through port and place them into the designated data VLAN.
So it handles untagged traffic for the data VLAN. What about the voice?
And for the phone's own traffic, the switch port needs to act more like a miniature trunk port, specifically for the voice VLAN. The IP phone itself is smarter. It's VLAN aware.
How does the phone know which VLAN ID to use for its voice traffic?
Usually through helper protocols like Cisco Discovery Protocol, CDP, or the Standardized Link Layer Discovery Protocol, LLDP. The switch uses these protocols to advertise the configured voice VLAN ID to the phone connected to the port.
Ah, the switch tells the phone, hey, use VLAN 20 for your voice.
Exactly. So the phone receives the PC's untagged data traffic on its PC-facing port and forwards it straight through, untagged, towards the switch, where it gets put in the data VLAN. But when the phone generates its own voice traffic, it tags those Ethernet frames with an 802.1q header specifying the voice VLAN ID it learned from the switch, say VLAN 20, before sending them down the wire to the switch.
Okay, this is a complex interaction for a single physical port. How do we actually configure the switch to handle these two different VLANs simultaneously, one untagged data and one tagged voice?
The configuration is layered, building on the standard access port setup. First, you define the data VLAN using the commands we already know. Switch port mode access to lock it as access for untagged traffic, and switch port access VLAN 10, assuming VLAN 10 is our data VLAN. This establishes the default broadcast domain for any untagged traffic arriving on the port, which will be the PC's traffic.
Okay, standard access config first, then we add the voice component.
Then you add the special command for the voice traffic, switch port voice VLAN 20, assuming VLAN 20 is our designated voice VLAN.
Just that one extra command.
Essentially, yes. That switch port voice VLAN command does several things under the hood. It tells the switch, expect potentially tagged frames on this port belonging to VLAN 20. It also triggers the switch to start advertising voice VLAN 20 via CDP or LODP to the connected device. When the IP phone receives that advertisement, it knows, okay, any traffic generated by my own CPU needs to be tagged with VLAN ID 20.
And that separation is critical for QoS, right?
Absolutely critical. When the switch receives a frame on that port tagged with the voice VLAN ID, VLAN 20, it can immediately recognize it as high-priority VACE traffic. It can then apply specific QoS policies, maybe trusting the existing QoS markings in the 802.1q header set by the phone, or placing it into a priority queue to ensure that voice traffic gets preferential treatment, minimizing latency and jitter across the network.
Now, the verification part here can be a bit confusing, can it?
Yeah.
If you run the standard show interfaces switch port command on a port configured this way,
Right. You might expect the operational mode to show something like hybrid or multi-VLAN, but it usually doesn't. The operational mode will still clearly state static access.
why? If it's handling tagged voice traffic.
Because the port's default behavior, the way it handles untagged traffic, is still that of an access port for the PC's data VLAN. The voice VLAN is treated as an exception or an addition on top of base access configuration.
Okay, so the operational mode says access, but how do we confirm the voice part is working?
The show interface's switch port output will provide clues. It will explicitly list both the access mode VLAN, for example, 10, and the voice VLAN ID, for example. Seeing both listed there confirms the dual administrative configuration of the port.
And what about trunking commands?
Interestingly, if you run show interface's interface trunk, even though this port isn't a traditional switch-to-switch trunk, you will often see both the data VLAN as the native access VLAN and the voice VLAN listed as allowed and active on what the command output might loosely term a trunk.
So the trunking verification command acknowledges the tagged voice traffic.
It does. It confirms the underlying mechanism. The tagged voice traffic is being treated very much like traffic traversing a tiny specialized trunk segment between the switch port and the intelligent phone. It's a really pragmatic solution that leverages the power and flexibility of the 802.1q standard for a very specific common access layer purpose.
Okay, here's where it gets really interesting, or maybe really frustrating. You've meticulously configured all these complex rules, VLANs, trunking, tagging, maybe even voice VLANs, DTP settings, and suddenly traffic just stops flowing for one group of users, or maybe for all users except those in the native VLAN. Troubleshooting layer 2 segmentation can be incredibly tricky because failures are often silent or intermittent or partial. We really need to focus on the common, costly misconfigurations that catch people out.
Absolutely. Our sources consistently emphasize starting with the absolute basics when troubleshooting VLAN issues. Step 1. Check access VLAN assignment and status. Don't assume the port is in the right VLAN just because the cable is plugged in.
This sounds almost too simple, but administrators frequently overlook one of two key things here, right? First, just verifying the correct VLAN is assigned using commands like show VLAN brief to see all VLANs and their assigned ports, or maybe show interfaces status, or show interfaces switch port for a specific port.
Correct. Double check the number. Did you type VLAN 10 or accidentally type VLAN 100? It happens.
And the second, equally critical check.
Ensuring the VLAN itself is actually active on the switch. A VLAN can exist, be defined, have ports assigned to it, but still be inactive.
An inactive VLAN is effectively a dead VLAN, isn't it?
It's completely dead. The switch will not forward any frames within that VLAN if it's inactive. A VLAN can be administratively shut down using either the global configuration command shutdown VLAN ID, like shutdown VLAN 10, or by going into VLAN configuration mode, VLAN 10, and issuing the shutdown command there.
How can you tell if it's shut down?
The show VLAN brief command is usually the quickest way. If you look at the status column for your VLAN and it says ACT, which means active local shutdown, that's your problem.
Okay, so even if the port interface is up, if the VLAN itself is shut down, traffic goes nowhere.
Nowhere. The ports assigned to it might appear to be working fine, link lights on, everything looks good at the physical layer, but the traffic just dies silently inside the switch because the logical domain is disabled. Always check show VLAN brief.
Okay, simple but crucial first step. Step 2 is about mismatched trunking operational states. We already talked about the relatively benign failure of dynamic auto facing dynamic auto, where they both just become access ports. But the worst case scenario, the truly insidious one, is the silent killer involving mismatched static or negotiated trunk access definitions.
Let's illustrate that silent killer scenario again because it's so important. Imagine switch A has a port explicitly configured as a static trunk using switch port mode trunk. It's happily sending all non-native VLAN traffic correctly tagged with 802.1q headers across the link.
Okay, switch A is doing its job.
But switch B on the other end of that same cable has its port accidentally configured as a static access port, maybe using switch port mode access and switch port access VLAN 1, or perhaps has left as dynamic auto and failed to negotiate a trunk with switch A's static trunk setting.
So one side thinks it's a trunk, the other thinks it's an access port. What does the link status show?
Physically, the link is usually up. Lights are green. An engineer doing a quick check might glance at it and assume basic connectivity is fine.
But it's not fine, is it? What traffic actually works?
Critically, traffic belonging to the native VLAN works perfectly fine. Why? Because switch A, being a trunk, sends its native VLAN frames untagged. Switch B, configured as an access port, say in VLAN 1, the default native, sees a normal untagged Ethernet frame arrive. It processes it normally within its assigned access VLAN, VLAN 1.
So ping might work if both switches have an interface in the native VLAN.
Exactly. Or CDP LDP might work if they run over the native VLAN. This gives a false sense of security. But the moment a frame from, say, VLAN 10 arrives from switch A, now properly tagged with an 802.1q header, because it's not the native VLAN, switch B receives it.
And what does switch B do with that tagged frame?
Switch B, operating as a simple access port, isn't expecting tagged frames. It sees this frame with an illegal, unexpected 802.1q header inserted, doesn't know how to process it, considers it a malformed frame and simply discards it, drops it on the floor.
Silently. No error message, usually.
Silently. So the result is that engineers will see some traffic working, specifically anything in the native VLAN, but traffic for all other configured VLANs completely fails to cross the link. It creates this baffling, inconsistent failure that can be really hard to pin down unless you specifically run show interfaces switch port on both ends of the link and compare the operational mode. If one says trunk and the other says static access, you found your silent killer.
And the fix is usually ensuring both sides match, both trunk or maybe trunk and desirable, or using a working dynamic pair like desirable.
Correct. Make the operational modes match and support trunking.
Okay, moving on. Step 3 involves managing the allowed VLAN list on trunks. By default, when a trunk link first comes up, it usually allows traffic for all defined VLANs, potentially 1 through 4094, to pass.
Right, the default is wide open. However, for security reasons, preventing unwanted VLAN traffic from traversing sensitive core links, or sometimes just for administrative tidiness and performance, engineers often restrict this list. They use the interface command switchport trunk allowed VLAN range. For example, switchport trunk allowed VLAN 10 million, 20 million, 30,000, 100, 110.
This acts as a crucial administrative filter, basically saying only these specific VLANs are permitted to use this trunk. But the actual process of traffic filtering on a trunk link is more layered than just this one command, isn't it? Which is why the output of the show interfaces trunk command is so incredibly valuable for diagnostics.
Absolutely. If we connect this to the bigger picture, the show interfaces trunk output essentially filters the potential VLAN list through 3 progressive stages or checks. Traffic for a specific VLAN must successfully pass all 3 of these checks on the sending switch to even be allowed onto the trunk link.
Can you walk us through those three lists typically shown in the show interfaces, trunk output, and what each one tells us diagnostically?
Sure. The first list you usually see is VLANs allowed on trunk. This reflects the direct result of that switch port trunk allowed VLAN command. It's purely the administrative configuration. If your VLAN 10 traffic isn't working and you see VLAN 10 is missing from this first list, then the problem is simple. An administrator explicitly configured the trunk to not allow VLAN 10. That traffic is blocked right at the source before it even gets considered further.
Okay, the administrative gatekeeper. What's the second list?
The second list is usually labeled something like VLAN allowed and active in management domain. This is where the switch checks its own local status for the VLANs that pass the first check. It takes that administratively allowed list from list 1 and then removes any VLANs from it that are either currently administratively shut down, active shut status, or simply haven't been defined, created in the VLAN database on this local switch.
Ah, so the VLAN has to be allowed and exist and be active locally.
Exactly. Traffic for VLAN 30, for example, might be listed as allowed on trunk administratively. But if VLAN 30 hasn't actually been created on switch A, or if it's currently shut down on switch A, then switch A simply can't process or forward traffic for it, so VLAN 30 gets removed from the second active list.
Makes sense. What's the third and final filter?
The third, and often most complex list to interpret, is LANs in spanning tree forwarding state and not crooned. This list takes the VLANs that are both allowed and active, past list 2, and applies the final layer 2 control plane checks.
Spanning tree comes into play here.
Right. If the spanning tree protocol, running per VLAN, remember, has decided to place this specific trunk port into a blocking state for a particular VLAN, say VLAN 40,
Right.
to prevent a network loop,
Mhm.
then traffic for VLAN 40 will not be forwarded out this trunk, even if it was allowed and active. It gets filtered out here. Additionally, if you were using VTP pruning, VLANs pruned by VTP would also be removed at this stage.
So if your VLAN 40 traffic is failing and you check show interfaces trunk and you see VLAN 40 listed in the first two lists, allowed and active, but it's missing from this third list, then your problem isn't likely the trunk configuration itself. You need to investigate your spanning tree topology for VLAN 40. Why is STP blocking on this port for that VLAN? Is there a loop? Is the root bridge in the wrong place? It points you towards STP troubleshooting, not trunk settings. That progression administrative allowed, locally active, and layer 2 control STP state is really the blueprint for systematic trunk troubleshooting. If traffic for a specific VLAN is failing to cross a trunk, you check those three lists in the show interfaces trunk output in that order to pinpoint where it's being filtered out.
Precisely. It narrows down the possibilities dramatically.
Okay, one last major troubleshooting area, and it's arguably the most severe from a security perspective. Step 4, mismatched native VLANs. We know the native VLAN is special because its traffic crosses the trunk untagged. We also know the default is usually VLAN 1. But you can change the native VLAN using the command switch port trunk native LAN ID, right?
Yes, you can, and often for security reasons, you should change it from the default VLAN 1. However, if you do change it, you absolutely must be obsessive about ensuring the native VLAN ID configuration matches exactly on both ends of the trunk link.
What happens when they don't match? Let's say switch A thinks the native VLAN is 10, but switch B thinks the native VLAN is 20 on the link between them. Why is this such a severe security threat, known as VLAN hopping?
Okay, let's trace it. A user connected to an access port in VLAN 10 on switch A sends a normal frame destined for another device also supposedly in VLAN 10. Switch A sees this frame needs to cross the trunk link. Since VLAN 10 is configured as the native VLAN on switch A's trunk port, switch A sends the frame across the trunk untagged.
Okay, untagged frame goes across, now switch B receives it.
Switch B receives this untagged frame on its trunk port. Switch B looks at its configuration for that trunk port and sees that its native VLAN is configured as VLAN 20. So switch B applies its local assumption. An untagged frame arrived on this trunk, therefore it must belong to my configured native VLAN, which is VLAN 20.
Uh-oh.
I was right. Switch B then forwards that frame into the VLAN 20 broadcast domain. The traffic has effectively instantly jumped from the VLAN 10 segment into the VLAN 20 segment without ever passing through a layer 3 router or firewall that would normally control traffic flow between those subnets.
That's VLAN hopping. It completely bypasses the intended segmentation and any layer 3 security policies between those VLANs.
Precisely. An attacker, if they can gain access to send traffic onto the native VLAN on one side, especially if it's the easily guessed default VLAN 1, can potentially craft frames, sometimes using double tagging techniques, which is a more advanced attack, to exploit this mismatch and inject their traffic directly into a different, possibly more sensitive target VLAN on the other side of the trunk.
That sounds really bad. What's the best practice to prevent this?
Several things. First, always manually configure trunk ports with switchport mode trunk to avoid DTP issues. Second, explicitly configure the same native VLAN ID on both ends of every trunk link using switchport trunk native LAN ID. Third, and very importantly, change the native VLAN ID away from the default VLAN 1 to some other unused VLAN ID, like 999 or 4000, for example. And fourth, crucially, ensure that no user access ports anywhere in your network are ever assigned to that chosen native VLAN ID. Make the native VLAN purely a control transit VLAN for the trunk itself, with no end devices in it. This significantly minimizes the attack surface for VLAN hopping exploits. #outro.
Wow, we've certainly covered a tremendous amount of ground today. We went from understanding the fundamental limitation of Layer 2 broadcast domains through the mechanics of 802.1q tagging and trunking, the complexities of DTP negotiation and voice VLANs, and finally into the critical, layered troubleshooting steps required to keep it all running smoothly and securely.
It's a lot, but to summarize, I think you really need to remember these three pillars. First, VLANs are the essential method for segmenting broadcast traffic,
Right.
primarily giving you better performance and security. Second, trunking, mostly driven by 802.1q tagging, is the essential method for scaling that segmentation across multiple physical switches and links. And third, meticulous attention to configuration details, especially the port modes, access versus trunk versus dynamic, the access VLAN assignments, the allowed VLAN lists on trunks, and very critically, the native VLAN setting is the only way to avoid those silent, frustrating failures and, more importantly, prevent critical security vulnerabilities like VLAN hopping.
So what does this all mean? Well, it means if you followed along, you now have the conceptual tools and the practical command knowledge to analyze the Layer 2 forwarding plane of a switched network with, hopefully, the precision of a seasoned engineer. You should be able to look at a failing link, run a few key show commands, and immediately start determining if the issue is likely administrative, like the allowed VLAN list related to local status is the VLAN active or shut down, a negotiation mismatch, DTP modes, or maybe a Layer 2 control plane issue, like STP blocking.
Absolutely. And for your final provocative thought today, something to mull over. Consider the implications of running common proprietary discovery protocols, like Cisco Discovery Protocol, CDP, over a trunked link. Now imagine a trunk connection fails to form correctly specifically because both switches connected are left configured in the default dynamic auto mode. We know this results in an operational access state on both ends. The link itself is physically up, CDP might even be exchanging information over the native VLAN, but no tagged VLAN traffic is actually moving across the link. Here's the challenge. What is the fastest way, using just a single show command that we reviewed today, to definitively prove that the failure is due to both endpoints operating in the wrong mode, access instead of trunk? And thinking logically, what is a single interface configuration command needed on your side of the link to fix the operational state and bring the trunk up, assuming you cannot log into or change the configuration of the neighbor switch? This requires putting together the DTP negotiation matrix we discussed, table 8.3 in many texts, and the output of the verification commands, like in table 8.4.
Interesting puzzle. Ponder that logical fix, combining negotiation behavior with verification. We'll catch you next time for the next deep dive.